Good morning, guys. Today we're going to be doing some more notes on gas volume and the relationship between moles and that volume. And these are related to sections 10.7 and 10.8 on CK12. So I think by doing notes, it might help us a little bit rather than just having you read it and then do the questions. Now I'm thinking maybe we do some notes and then you do the questions and we'll see if that helps with the CK12 situation a little bit more. So first we're going to talk about conversions between moles and gas volume, and we kind of talked about this in the last notes section that we did. Molar volume is the STP, standard temperature and pressure. It can be used to convert from moles of gas to volume and from gas volume to moles. 1 mole is equal to 22.4 liters at standard temperature and pressure. In the previous notes, we talked about how standard temperature and pressure means 0 degrees Celsius and 1 atmosphere, or 101.3 kilopascals. In this equation, or this equilibrium of 1 mole being equal to 22.4 liters, is the basis for the conversion factor that we will be using. So here we have a sample problem where we want to convert from volume to moles. And it says many metals react with acids to produce hydrogen gas. And if you remember way back when, I think it was second quarter, we did a lab on the reactivity of metals. And really it was the reactivity of elements on the periodic table, and we were talking about that. And one of the things that you did was you put a strip of metal in sulfuric acid. And what a lot of you noticed was that bubbling occurred. That bubbling was the production of hydrogen gas. So a certain reaction produces 86.5 liters of hydrogen gas at standard temperature and pressure. How many moles of hydrogen gas were produced? So our first step in this is to list our knowns and our unknowns. So we know that we produced 86.5 liters of hydrogen gas, H2. It's H2 and not just H, because remember, hydrogen is one of the 7 diatomic elements. We also know that 1 mole of gas at standard temperature and pressure, which this problem states this occurred at standard temperature and pressure, is equal to 22.4 liters. Our unknown is how many moles of H2 were produced. So we have 2 options for a conversion factor here. We know that 1 mole is equal to 22.4 liters, and that gives us 1 mole over 22.4 liters, and it also gives us 22.4 liters over 1 mole. Since we're starting with a known of liters, and you can imagine this as 86.5 liters over 1, we want to convert to moles. So this liters unit we want to get rid of. In order to get rid of units, we do have to have the same unit on the opposite side of that fraction line. So if this is in the numerator, we want liters to be in the denominator. So we go ahead and choose the first conversion factor, 1 mole over 22.4 liters. Now we can actually calculate. So we have 86.5 liters. We're going to multiply that by 1 mole and then divide by 22.4 liters. This way our liters cancel out. We end up with moles. And if you plug that into your calculator, 86.5 divided by 22.4, you get 3.86 moles. So that's how many moles of H2 gas were produced in that reaction. Another problem we could get from this is kind of going the opposite way, going from moles to volume. So what volume does 4.96 moles of O2 occupy at standard temperature and pressure? So again, 2 important things to note. O2 is a diatomic element, so that's why it exists as O2 and not just O. And our STP. STP means that we can have this conversion factor of 1 mole compared to 22.4 liters. So again, we're listing our knowns and our unknowns. We know we have 4.96 moles of O2. We know 1 mole of gas is equal to 22.4 liters. And we want to know what the volume of O2 is in liters. There's multiple units you could have for liters, one being, another common one being milliliters, But since this 22.4 is listed in liters, that's how we know what unit our volume will end up being in. So now again, we have to determine what conversion factor we're going to use. And we have those same two options, 1 mole over 22.4 liters or 22.4 liters over 1 mole. To decide this, I'm looking back at our known. It's given in moles, and I'm looking at what we want to find, which is volume in liters. So since we're given something in moles, that means we want to cancel out this mole unit in order to get liters as our final answer. So we're going to go ahead and go with the second conversion factor, 22.4 liters over 1 mole. So when we calculate this, we're taking our 4.96 moles of O2 gas, multiplying it by 22.4 liters, and dividing by 1 mole. This conversion factor helps us to cancel out those moles so that our final answer is in liters, and we get an answer of 111.1 liters. And here's another problem that we can do, and this is going from volume to mass. Now, there's no one direct conversion factor that relates volume and mass. We only have a relationship between volume and moles. But what we do have is a relationship between moles and mass in grams, and that comes from the molar mass of elements and compounds. So we're going to end up using two conversion factors to kind of figure this one out. If you think of your roadmap, it's like when you have to go through two roads to get to that answer. In this case, we're starting with volume, then we're going to moles, and then we're going to mass. So you could add this volume conversion to your roadmap, okay? So you could add volume as another unit off to the side, like I think there's room up top if you want to do that. And you would have an arrow going from volume to moles, and an arrow going from moles to volume. And again, you have these two conversion factors, one for each of those arrows. So first thing we have to do is determine both of our conversion factors. Here, since we're starting with 867 liters, I know we want to get rid of liters, and liters here is in the numerator. So I'm going to use the conversion factor with liters in the denominator, which is this first one, 1 mole over 22.4 liters. Second conversion factor I have to determine has to do with the molar mass of N2. And we find that on the periodic table. Molar mass of nitrogen times 2, because again, nitrogen is a diatomic element, so as N2 is what exists in nature typically. And this relationship gives me that there are 28.02 grams per 1 mole, or that there's 1 mole in 28.02 grams. And here, remember by my first conversion factor that I found, my unit is going to end up being in moles. My final unit needs to be in grams. So I have moles on the numerator once I do that first conversion, and I'm going to want to cancel out with moles in the denominator. So I'm going to go ahead and again choose that first conversion factor to get moles in the denominator to cancel out my units. And now I can set up using dimensional analysis to solve our problem. So we're starting with 867 liters. We're multiplying by 1 mole, dividing by 22.4 liters. So that helps to get rid of the liters unit, and we end up with moles. And then I'm using our second conversion factor, 28.02 grams over 1 mole. That gets rid of our mole unit, and my final answer will be in grams. So if you put this into your calculator, 867 times 1 divided by 22.4 times 28.02 divided by 1, you should end up with 1,086.6 grams of N2 gas. Okay, so I'm not going to go through the answers of all these I'm not going to go through the answers of all these review questions, but I will kind of talk about how you think about them, how you set them up to solve them. So in the problems above, why is the gas always at standard temperature and pressure? Remember that conversion unit we have, that 22.4, is only true at standard temperature and pressure. So if we had something at 100 degrees Celsius, which is not standard temperature, could we use that conversion factor? Number 2, A container contains 45.2 liters of N2 gas at STP. How many moles of N2 gas are in the container? Okay, so here in this problem, we are going from liters to moles. So that's going to be using one conversion factor. Hopefully you know what conversion factor that would be. And for the third review question, if the gas in the previous problem was CH4 instead of N2, then how many moles of CH4 gas would there be? Going from volume to moles, did we use molar mass? So would that change your answer at all? Something to think about. Next, we're going to talk about gas density. So if you've ever been to a party or thrown a party, you've probably had balloons. With those balloons, if we want them to float, we always have to buy helium to fill them up. Because if you notice, if you blow them up with your own breath, they don't float, they sink. The reason for that is that those gases have different densities. So density is defined as the mass per unit volume. So usually we see it reported in grams per liter or grams per milliliter. The density of gases is determined by the molar mass of that gas. So a gas with a smaller molar mass will have a lower density than a gas with a large lower mass. Gases with that are less dense than air, like helium, what we use to inflate party balloons, will float or rise. Whereas gases that are more dense than air, like CO2, which comes from your breath when you blow up a balloon, will sink. Gas density can be calculated from molar mass and molar volume. So this first problem, what's the density of nitrogen gas at STP, standard temperature and pressure? First, we have to list our knowns and our unknowns. Remember from the previous problems, we remember that nitrogen is diatomic as a gas, so it only exists as N2. So nitrogen's molar mass is 28.02 grams per mole. We also know that at standard temperature and pressure, 1 mole of gas is equal to 22.4 liters. So how can we calculate the density of that gas, which will end up being in grams per liters? Here it's again kind of all about canceling units. Our two knowns here, we have grams per mole and we have liters. Basically what we want to do is cancel out this mole and end up with liters to get grams per liters. So we're going to start with the known molar mass of N2, 28.02 grams over 1 mole. And then to cancel out the moles, we're going to end up putting the moles on the opposite side of the fraction line in order to cancel units. So since mole is in the denominator here, we're going to want it in the numerator for our conversion factor. So what you'll notice is that the moles cancel out and our answer will be in grams per liter, which is the exact unit we want for density. So in your calculator, you plug in 28.02 grams over 22.4 liters, and you end up with 1.25 grams per liter. We can also have a problem where we're looking for molar mass given a gas's density. So we want to know the molar mass of a gas whose density is 0.761 grams per liter at standard temperature and pressure. So again, we're going to list our knowns and unknowns. Density is in 0.761 grams per liter. At standard temperature and pressure, we know that 1 mole is equal to 22.4 liters, and we are solving for molar mass, whose unit is in grams per mole. So again, here we have a known that's in grams per liters. We have a conversion factor that converts liters to moles, so we can easily change this bottom unit of liters to moles to get grams per mole. So we're going to take our 0.761 grams over 1 liter, and the conversion factor we're going to use, we want liters on the opposite side. So we're going to multiply this by 22.4 liters over 1 mole. That way our liters cancel out. Our final answer will be in grams per mole, which is what we want. So we take 0.761 times 22.4, and we get 17.0 grams per mole for the molar mass. These review questions. How is density calculated? Okay, what is density? It is the mass over volume. How is molar mass calculated? What special table do we use to find molar mass? And what would the volume of 3.5 moles of gas be? Here there's only one conversion. We're going from moles to liters. What's the great conversion that we've known at standard temperature and pressure?